What up? We're going to be taking a look at the end behavior of these things, and I'm going to go pretty quickly. We're going to try a few of them. This negative bx is equal to negative, or bx is equal to negative 2x to the fourth plus 5x minus 9. We can kind of disregard these last terms because the only important term here is the leading coefficient. It's the one that has the biggest exponent. So you know that that's the one that's going to play the biggest role when we're talking about really, really large x or really, really small x. And if you know how to graph x to the fourth power, which is pretty simple, it could look something like this, but technically, actually, x to the fourth power doesn't look exactly like that. It would look something like this. It's almost like a steeper parabola. Oh, wait a second. I need negative 2, so my actual graph should look something like this. And I don't know if that's what the middle is going to look like, and I don't really care because the game that we're trying to play here is end behavior. So I know that the end behavior of this thing is going to look like that and that. So I would say that the end behavior looks like this. I'll tell you what, why don't we check it out and see if we can get the computer to agree with us, and we'll see what happens. So I'm arguing with you that negative 2x to the fourth power plus 5x minus 9. All right, let me zoom in a little bit. There we go. It almost looks a little funky, and it's got this extra little bump over here. And if I want to even compare that to negative 2x to the fourth power, I know, obviously, yes, I agree. Oh, I'm sorry. There's a 2 out in front. There we go. I agree with you that this purple graph doesn't exactly look like the green graph. However, if I zoom out enough, you can barely tell the difference. Because essentially, when you're talking about the end behavior, where does it look like as it goes out to x is equal to positive 100 and x equals negative 100, or positive 1 million or trillion billion or a Google or whatever, or Googleplex that big and a negative Googleplex. We're talking about, yeah, that would accurately describe how this thing looks. All right, let's do this one. This thing is x to the 6th minus 7x squared plus 8x minus 1. All right, basically you just kind of scrub that off and you say, hey, x to the 6th power, that could look like this. But really, I don't care what it looks like in the middle. I just want to know what it looks like at the end. There we go. All right, negative 5x to the 5th power. Okay, so scrub this off because the leading coefficient is x to the 5th power, and so I know that x to the 5th power could look something like that. I don't really care what the inside looks like, but it's negative, so I know that it's probably going to be looking something like this. Here's the x-axis. Here's the y-axis, and my graph is going to go up to infinity on the left side, but down to the infinity on the, or down to negative infinity on the right-hand side. Why don't we try graphing that and seeing if that works? So I graph, and you don't need to graph this. I'm just kind of showing you, proving to you that what I'm talking about is not crazy, or at least I hope I'm not crazy. Plus 8. There we go. So you can kind of see how it's got these extra bumps, and that would be x to the 5th power. But it actually did exactly what I told you it would do. On the left side of 0, it goes up to infinity. You see it? And on the right side of 0, it goes down to negative infinity, which is exactly what I have here. So my end behavior was correct, even though technically I didn't get what the middle looked like, but that doesn't matter. Or at least it doesn't matter to me. All right, let's see. Is this a problem I want to do? Sure. Yeah, sure. Nah, no. I'll wait for the next one. All right.